Let's see how well this goes. All right, so in this section, we're covering single equations, not systems yet, first order differential equations, and now we're going to look at ones that involve nonlinear differential equations. Now, you'll recall back at the very beginning of 1.3, our very first, very simple linear model was one called the, well, it was population dynamics. I don't even know if I gave you this name or not. The guy who's it's named after is called Malthus. His last name was Malthus, so it's called the Malthusian model, Malthusian model. But the Malthusian model, we assume that population growth is proportional to the population, namely dp dt is equal to kp. Another way of looking at this is that if you look at the ratio between dp dt and the population, that they stay in constant proportion to each other. All I'm doing is dividing the p to the other side, but that's what proportionality basically means, is that the two quantities, if you take the ratio, stays constant. You double one, the other has to double. Right? If you triple one, the other one has to triple. It stays in constant proportion to each other. Okay? Well, the question now becomes, what if the ratio between the rate and the population is not a constant, but maybe depends on some other mechanism? And we're going to start with those mechanisms being something that doesn't depend on time. So let's say we have dp dt divided by p is some new function of p. Okay, where this depends only on p. And what do I mean by time-independent mechanisms? Well, one of the simplest ones is the first one we're going to look at is, what if in addition to the fact that the population grows at a rate proportional to how big it is, that there's some limit to how big your population can get? Obviously, that's going to be the case in almost every real circumstance, whether you're talking about bacteria on a petri dish or you're talking about humans on the face of the globe. There's going to eventually be some carrying capacity where we can't grow exponentially forever. We reach an upper limit on not only how much space there is, but maybe how much resources there are to support that population. And so the idea of a carrying capacity doesn't depend on time, right? It only depends on how many people are there. The closer you get to the carrying capacity, your rate of growth is going to decrease. And so what we're going to look at is a model called the Logistic Model, or Logistic Equation, where we assume that a population can have no more than some number of individuals in, which we're going to refer to as our carrying capacity. Okay? So how do we do that? Well, it's that same idea of what I just said. It's going to grow proportional to the size of the population, but also as we get close to the carrying capacity, that growth rate should slow down. So one way to do that is to assume that your rate of population growth, dp dt, is jointly proportional to first p, which is exactly what the Malthusian model says, and this is the choice that makes it a logistic equation, your distance from the carrying capacity. Right? As you get closer to that, right? If say, just for some numbers throwing out here, let's say our carrying capacity is 1,000 individuals. Right? When you're down at 1, 2, 3, you're a long way from your carrying capacity, right? So your rate of growth is still going to be high. But as you approach your population, your carrying capacity, if you get up to the 900 range or 950 range, that number, n minus p, gets smaller and smaller, and so your rate is going to begin to decrease as you get closer to it. Does that make sense? So how fast your population is growing will begin to decrease as you get closer to your carrying capacity. Now, this term jointly proportional, you've probably seen in algebra before. So when you talk about jointly proportional, that just means it's proportional to both or the product of those two. You can write that as now an equation. If I say one variable is jointly proportional to two others, it's just that variable equals k times their product. So dp dt is equal to k as a constant of proportionality times one variable times the other variable that it is proportional to, jointly proportional to. So now we have a new differential equation. Kp times n minus p. Now is that linear? And why not? I saw some shaking heads, by the way. P squared, nonlinear, right away. So this is going to be a nonlinear model. By the way, while this is a good starting point, it's much more common to approach this in a slightly modified way. So the more common approach, that's approach, by the way, A-P-P-R-O-A-C-H, I ran out of space. A-P-P-R-O-A-C-H is to look at it this way. Distribute the k inside. So you have dp dt equals p times a kn minus a kp. And instead of calling these in terms of k and n, we're going to refer to this as a, and we're going to refer to this as b. All I did was distribute the k inside, by the way. And so what we're really going to look at as the logistic equation is one in the following form. It is dp dt is equal to p times a minus b times p. By the way, we've seen that before. Does anybody recognize it as an example that we might have covered before? Or when we talked about it?
Can we talk about it in phase portraits?
Phase portraits, right? Because we had those two unknown values in there, and we still were able to construct a phase portrait based on known values of A and B. And by the way, in this case, K is always positive. So our Kn, which is A, is positive, and B is positive. So we're going to assume A and B are positive, just like we did when we were constructing phase portraits for this particular autonomous differential equation. All right, let me grab the next page. All right. So if we want to find the solution to the general logistic equation, we notice that it is separable. Even though it's not linear, it still is separable. Because all autonomous differential equations are separable. But when we separate it, and all I'm going to do to separate it is I'm going to take all of this and move it over to the left-hand side and take the dt and move it over to the right-hand side, you end up with this integral right there. The integral of dp over p times a minus bp equals the integral of dt. So to integrate the left-hand side, that's where we need partial fractions. Integrate 6 over x squared plus 2x minus 8. All right, so what's your first step if you're going to integrate that? You obviously can't use substitution, because if you did use substitution for the denominator, you would need an x term on top, right? And you don't have an x term on top. And you need a constant term on top, which we do, but we can't just use substitution. So factor the denominator. This is 6 over plus minus 4 and 2 works, right? So now, take 6 over x plus 4, x minus 2, and set it equal to something over the x minus plus 4 term plus something over the x minus 2 term. And the goal is to find what the a and b are. Vaguely familiar? Knocking those cobwebs off up there. What I do is I simplify this by multiplying through by the common denominator and write this as 6 equals a times x minus 2 plus b times x plus 4. Right? I am thinking of this as multiply through by x plus 4, x minus 2. And then you got one equation with two unknowns. We really just got to find any two values that work. So I am going to just pick values for x, right? It has to be true for all x. So let's let x equal 2. Why did I choose 2? Zero's out the a. 6 is equal to b times 6. So b has to be 1. What if I let x equal negative 4? 6 has to equal a times a negative 6, right? And then plugging it in over here gives me 0, so it zeroes out the b term. So a has to be negative 1. All right, so plug that all in. That means this integral right here is the same thing as the integral of a over x plus 4, which was negative 1 over x plus 4, plus b over x minus 2 dx. I have split 6 over x squared plus 2x minus 8 into those two fractions. If I were to add them up algebraically, I would get the original integrand. But now I can integrate both of these simply. All right, the integral of negative 1 over x plus 4, negative natural log of x plus 4, plus the integral of 1 over x minus 2 is the natural log of x minus 2 plus, of course, c. That's how partial fractions works. But you knew that already. But it's a good refresher. So now what I want to do is exactly the same thing, but with my logistic equation, the integral that I needed to solve it. All right. Let me go grab my slide for that. Is that the right? Oh. All right, so now consider the left-hand side of equation 1. And let's do that with partial fractions. Did everybody finish the previous slide, or do I need to go back? We good? Okay. So 1 over p times a minus bp equals something over p plus something else over a minus bp. I got to find my capital A and my capital B. What would I do first? Multiply through by that denominator. So I write this as 1 equals, and then the p cancels, and I'm left with a times a minus bp plus, and the a minus bp cancels, and I'm left with b times just p. So like we did before, let's choose values of p. This has to be true for all p, since we want this to be an identity. We want that first equation to be true no matter what p is. So let p, what would you choose first? 0 is an easy one. So that means a times a minus 0, so just a, right? Little a. Plus b times 0. Y'all agree that's what I get? Plugging in 0 for p means capital A is 1 over little a. Now we could plug that in and solve for p, or actually let's just do what we did before. What's another good choice? Can you see one that would zero out the first term on the right hand side? I think a over b works, right? Because the b's then cancel, you have a minus a. So let's do a over b. I'll write this fully out, equals a times a minus a, b times a over b plus b times a over b. And this goes to 0. So b is b over a, right? So take both of those, plug it in here, and you've got 1 over a divided by p plus b over a divided by a minus bp, right? Just stick those up here where a and b are. All right, so that means the integral of 1 over p times a minus bp dp is equal to the sum of two integrals now. It's the two integrals I have right here, or the two terms right there that I want to integrate. So here's how I'm going to write that. I'm going to do the integral, and I'm just pull that 1 over a out front because I like writing it that way better. Plus, and I'm going to do b over a times 1 over a minus bp dp. Right, so that original integral that I wanted to take, I can now write in that way. So you end up with 1 over a times the natural log of p plus, you'll have the b over a still out front. And what's the what's the integral of 1 over a minus bp? Integral of 1 over a minus bp dp, negative 1 over b, natural log of a minus b capital P. All right, so that equals a negative 1 over b times the natural log of a minus bp. Plus c, which actually I'm going to put the plus c on the other side, because I still have the right-hand side of the integral on equation 1. Right, so plus c here, there's going to be a plus c when I do integral of dt. So I'll do that on the other side. So this right here cancels. So I tell you what, let's draw a line here and write this whole thing out what I've got. From equation 1. From 1 plus the integral that I just got, I have that 1 over a natural log of p minus 1 over a natural log of a minus bp is equal to, and the other side was the integral of dt, right? Back on equation 1, you can look up higher on the page, equation 1, the right-hand side is integral dt. What's the integral dt? T plus the constant. So this is equal to t plus c. And again, this just comes from the integral of dt. All right? You believe me? Follow me? It's just integration by parts to get the left-hand side. And actually, what I can do here is I can simplify this a little bit. First, let's simplify it by moving the a to the other side. Just multiply everything through by a. Actually, I tell you what, flip over to the next page. Instead of writing that down right there, we have the following. That's what I have written at the top of the next page, isn't it? Exactly what we just came up with here. So, let me jump to the next slide. Go grab that page. Hopefully it's this one. Done? Is that it? Yeah, perfect. So let's solve for p. I'm going to multiply through by a, which gives me natural log of p minus natural log of a minus bp equals at plus ac, or just a constant, right? A constant times an arbitrary constant is still just an arbitrary constant. As long as I don't introduce any more t's, I'm just going to keep calling it c. And what can I do on the left-hand side? You remember the property of logs if you have the difference of two logs? Divide them. It's the log of the quotient. The difference of the logs is the log of the quotient. Natural log of p divided by a minus bp equals at plus c. And now, trying to solve for p, I'm trying to get p by itself. Yep, exponentiate both sides. E. Split this up to times e to the c. On the left-hand side, those cancel, so I have p over a minus bp equals, we'll call this just some new constant c, so ce to the at. So let's multiply by a minus bp on both sides. So I end up with p is equal to this right here. I'm just going to distribute so I have space. I'm going to scribble this up here. If I had c e to the at times a minus bp, if I distribute this, I have a c e to the at minus b c p e to the at. And again, because I'm trying to get p by itself, that's why I multiplied this out. I'm going to take this guy right here and move him back over to the other side. Right, and factor out the p, which they both have in common, and then divide that thing off. So that becomes p, I'll come down here and write it, minus bcp e to the at equals ace to the at. If you factor out the p, that's 1 minus bce to the at plus, very good. Yes, absolutely. ace to the at. Okay. Divide that across. P is now equal to ace to the at divided by a 1 plus bce to the at And to get what we normally would write as the logistic equation, I'm going to multiply this so that there's only one e term in here. If I multiply the top and bottom by e to the minus at on top and bottom, so I don't change the value of the fraction, I end up with this. Instead of taking the time to do it in the lecture, I'm going to let you assume that the process is exactly the same with a lot of algebra involved, right? What's the process for finding the C? Plug in your initial condition. So you're going to make this on this side equal P naught. Put in a 0 here, so that just becomes 1. And solve for C. And you do the same trick of multiplying across the other side, gather the C's together, factor it out, move it across, plug it back in. So with all that extra work, which is the next gap you have on your page, you can just write S-A-O-H, right? Some algebra occurs here. I'm getting lazy, my old age. Oh, undo, cancel. Next slide. Right, so it ends up being P naught equals AC over BC plus 1, right? Solve for C. Turns out C, by the way, equals P naught over A minus B P naught. But then I plug that all into here. And simplify, and guess what you get? You get this guy right there. Booyah. It is, from the original problem, if your differential equation was P times A minus BP, then AP naught over BP naught plus A minus BP naught e to the minus AT. All right, now what I've got on the next two slides are examples. Okay? Actually a couple of questions, but mainly two examples that I work so that you can see how to do these problems in your homework. So, I'm going to work those two examples in another video for you, but it's basically applying what we've already done in 3.1, which is using the information that's given in a problem together with this equation right here. Right? I'm going to give you different things like P naught, A, and B. In some cases, I'll give you different pieces of information, but this is the model equation you have to work with to be able to solve the logistic model word problems. Okay? So, I'm not going to check that you've watched the video. I'm just going to assume that if you want to know how to do your homework, you'll want to see some examples worked. So you can go watch the videos for these two examples that are on the next pages of your notes. Fill those in. But don't forget that because we don't have class on Thursday, you have to watch the 3.3 video, fill in the notes, and get that back to me. I'm going to push all the dates for everything that's assigned right now, which is 3.1, 3.2, and 3.3, all till after spring break. But you'll still want to start working on them as soon as you're ready, okay? That's all I've got for you. We will see you after the break.